Hi everyone. Today what we're going to be looking at is what we kind of refer to as a little bit of a combo day. So if you want to kind of call it a bit of a review day, maybe you're thinking of it as review, but really what we're going to do is we're going to put together a bunch of stuff that we've dealt with over the last couple days. So because we're putting everything together, I wouldn't call today like a straight review. So this is not for like okay, I'm still trying to find my way through stuff sort of person. This is, I've got all the basics down. What I'm looking to do is to put it all together and see where we can take it in some kind of problem solving situations. So I want you to match up with our handout. You can see the first problem on the top of our screen right now. Everything today is going to be stop and give it a try on your own. So I would like everyone to pause that video and I want you to go ahead and tackle A. Okay, pause it now. Okay, we're back. So the first thing that should have been automatic for us was that we needed to look and see what were the factors on that denominator. So I am hoping that your first instinct was very automatic and it was I factor all the bottoms. Now, they're all simple trinomials, so that shouldn't have taken us too long. Honestly, it's probably longer to write it than it is to actually think about it. Okay, now that we have all of that, now we should be good to get a common denominator, and I would love it if we just put everything over one denominator right now. I need everything from the first denominator. Then I'm going to need whatever's different with the second denominator, so I need to put in another x plus 3. And I love the fact that I already have the third denominator mixed in there. So now my job, change all the tops the same way I changed the bottoms. So my old top was 3x. What's different between the two denominators? The x plus 3, I need to multiply that top by that. Now I have my old top of minus 4x. What's different between the denominators? It's that factor of x plus 1. Put it in there. My old top of 5x. What's different in my denominators? The factor of x plus 2. Multiply it in. So now I have an equal expression. The only thing is just simplify everything now. So I'm probably going to spend a safe line going through and expanding everything. I'm being relatively careful about my signs, slowing down where I know I make my common mistakes. The biggest pain is you're like, ugh, I just have to keep writing that denominator down. Okay, I'm going to shrink that a little bit just to give us a little more room. So now I can collect on top, and when I do, I'm going to end up getting a 4x squared. My single x terms, I've got 9 subtract 4, so there's a 5, plus a 10. There's my 15x. And I get down to that, of which I can take a quick peek on top and recognize, first off, if it does factor, I have a common factor of x. But I don't have a common factor of x on the denominator, so I don't care. And when I do, I'm going to now have my x and a 4x plus 15, of which that does not share a common factor on my denominator, so I know that I am done. So I get down to that point. The only thing I have to remember is tack on my restrictions, and we should have been good for x to not equal -2, -1, or -3. So hopefully on this first one we matched up and we just saw that we were going ahead and adding a couple numbers together. So now let's take kind of the next step. Rather than doing kind of the same operation, let's try to mix in some different operations. You can take a look at the expression that I've given you in B. You'll notice now we got some brackets in there. We've got subtraction and some division, a mixture of operations. Same thing as the first one. What I want you to do is I want you to go through and get a full solution to this thing, fully simplified. Okay, pause it now. Okay, we're back. So same thing as always. First step, let's factor everything and see what makes up each of those denominators. So on my denominator here, I've got a complex trinomial. So I'm going to work over here on the right side. I need two numbers that multiply to give 2, two numbers that multiply to give 3. If that's a negative and that's a positive, then I get my negative 5 in the middle. So I can factor my 2x plus 1 times my x minus 3. Now I have all inside this big bracket. Well, the next one just happens to be a difference of squares. So there's my x plus 3 times x minus 3. And now I'm going to go through and I'm going to do my fast factoring chart in blue. On my denominator, I'm going to have two numbers that multiply, two numbers that multiply. Both of those adding is going to give me a 7 in the middle. But at the same time, I'm going to flip and multiply. So I'm going to have a 2x plus 1 on top and an x plus 3. And then my x plus 4 will be on my denominator. So I know at some point to divide that fraction, I'm going to have to flip and multiply. I might as well do it right away. Okay, that would be my first line. Now I have everything broken up and I can see what makes up every fraction. Okay, I got to go through and deal with some BEDMAS. So I've got some brackets there. That means that I need to work through that subtraction operation first. So I now have big brackets here, and I'm going to put those big brackets in as square brackets just to be able to tell everything apart. My common denominator between those two fractions is all of the first, and I need what's different in the second. So what's different between my first denominator and my last denominator? Well, it's that x plus 3, so I have to multiply that top by x plus 3. What is different? Well, I've got that 2x plus 1 factor, so I need to multiply my old top by 2x plus 1. And that still then has to be multiplied by 2x plus 1 times x plus 3 all over x plus 4. Okay, I think we get to a little bit of a moment of reckoning, if you want to think of it that way. Is that we can go through, I'm just cleaning up that 1 there. We can go through and we can do a number of things at the same time. What I'm hoping that we can see is that we have one numerator that's unsimplified. So I cannot divide out common factors because those are not factors. However, the other parts of those fractions are all factored. So anywhere where I can divide out those common factors, then I can do that now if I like. I don't have to wait. So what you're going to see me do is I'm going to divide out whatever common factors I can. So I will notice that I have a 2x plus 1 and a 2x plus 1. Those are separated by two fractions that are multiplying, and they're on opposite sides of my division. So I can divide out that common factor. I can do the same thing with my x plus 3. I can get rid of all of that stuff. Well, at the same time, what I'm going to do is I'm going to expand and collect like terms with that numerator. Okay, here we go. So my numerator then is going to have to be my 3x squared plus a 9 minus a 2, so plus a 7x minus 6. And now I can expand my next one. I'm going to get a 2x squared, subtract it. My middle term would end up being a 5x, subtract it. My constant's going to be a 2, subtract it. Now I don't have to blindly copy everything out. I can see that all I have is an x minus 3. And I need to multiply that now by a 1 over x plus 4. So I at least save some time of having to go through and just copy stuff down. Okay, that big ugly numerator, I need to collect like terms. When I collect on that, I'm going to get down to that trinomial. And I'm hoping that even like as you're writing it down, we can already see where we're going to go. So there we go. We're shrunk a little bit. So we can take a look at that trinomial that we have on top, and we notice that that trinomial is going to factor. And we love the way that it factors. Because now my x plus 4 factors will divide out, and I can shrink that whole thing down to an x minus 2 over x minus 3. Nice. Okay, I'm going to argue that in this context, we've got a lot to consider as we go through to find our restrictions. So I am looking at all my denominators, but because that last fraction was attached by a divide by, that means I need to take into account all parts of that last fraction. So for me to state all my restrictions, I'm just going to work my way left to right. I know that x cannot equal negative 1/2. I'm going to go down below 3. I can also see that I'm going to have my negative 3, so I have a plus or minus 3. And then my negative 4. Notice the top of that last fraction, once I flipped it, I've already taken into account both of those restrictions. There we go. So hopefully we match up, and now we're starting to get comfortable working our way through dealing with multiple operations. Okay, let's try another one like that. Okay, so what you can see, we've got an expression sitting in front of us with different operations. So I want you to do the same thing. Let's work our way through final simplified form. Pause the video now. Okay, we are back. So I'm going to argue to you that if the first line was not automatic, I think that's telling us that we're missing a pretty big concept. So we take a look. We're going to want to factor everything. So I'm going to go through and factor all my denominators. 2 of my denominators are complex trinomials, so I'm going to have to do some fast factoring. So off on the side, I'm going to deal with my first one. 2 numbers that multiply to give 2. 2 numbers that multiply to give 15. And if both of those are addition, then I have my 11 middle term. So my denominator can then factor, oops, see I was about to write an x. There isn't any x's in that expression. A 2a plus 5 and an a plus 3. My numerator, there we go. My second, well, I need 2 numbers that multiply to give 6, so let's try that. 2 numbers that multiply to give 25, 5 and 5. I need a positive 5, so my 15 is positive, my 10 is negative. So I'm going to get a 3a minus 5 times a 2a plus 5 and my old top. And now same thing as we discussed earlier. So I'm going to take a peek and I'm going to change that to a multiply. My 2a will then be my new denominator, and I can common factor out an a from the top and be left with 3a minus 5. Okay, I think your only big mistake right now is to go through and really start to look for common factors. Make your focus be your operations. So we take a look here, and with what I've circled, I am hoping that you are not getting a common denominator between the first two, because you notice that when you take a peek at those operations, you have subtraction and you have multiplication, and BEDMAS says that you have to do multiplication first. So can you see the trap with that expression? We may have just worked left to right, and all of a sudden we're breaking BEDMAS. We need to make sure that we are following our order of operations. So I have to just leave that first fraction. I can't touch it. It is going to be my 3a plus 2 all over. And now I can reduce my next. So I take a peek at that and I notice that I have a 3a minus 5 and a 3a minus 5 common factor. Those will divide out. Well, I also notice within my last fraction, I have an a common factor that will divide out. Well, I don't have anything else in common in those last two, so I'm going to subtract an a minus 2 on top and a 2 times a 2a plus 5 on the bottom. So hopefully we matched up, we're good. If we made the mistake on BEDMAS at the beginning, like you should let out like an audible, oh, I can't believe I fell for that. But I also want to give you a chance to just pause the video now and see if we match up as we finish off. Okay, you're going to pause it if you needed to make an adjustment. Otherwise, we're all working along to our next line. So now I take a peek, and I'm just down to a straight subtraction question. So I need my common denominator. I need all of the first and whatever's different in the last. I can see both my denominators in there. I have to take my old denominator of 3a plus 2, and I need to multiply that by what's different. That means I need to multiply that by 2. I now have my old numerator of a minus 2, and I need to multiply that by an a plus 3. Okay, I can expand my brackets on top. So I'm going to get a middle term of positive, subtract it. I'm going to get a final term of a negative 6, subtract that. And so we should come in on that, of which I can fully go through and simplify that top. Now I'm going to write it in descending order, just because that will make it a little easier to see if it does factor further. And I get down to that. So hopefully not too bad, and we were able to go through and match up and everything was good. Now you take a quick peek at that numerator, and pretty quickly we should be able to see that that is not going to factor further. Even ignoring the signs on stuff, I don't have two numbers that multiply to give 10 and add to give 5. That is fully reduced. So only thing I need to do, just make sure I've got my restrictions. I'm going to look at my first factored form, and I notice that my a value, yikes, cannot equal negative 5 halves, negative 3, 5 thirds. I already have a negative 5 halves. My last fraction was dividing, so I need to make sure I take into account all parts, and that's what's going to require me to tack on that 0. So again, hopefully not too bad. And we won't fall into the trap of just working left to right, but instead our focus becomes what operations are there. So if we're good with that, then what I want to do is I actually want to spend the rest of the time today kind of working through what I would call some problem solving. So we're going to get into some instances. It's all based on the same theory that you have, that you've covered in previous years, that we've addressed in this year. But can we put it into a slightly different setting? Okay, we need to have the proper mindset. The rest of today is problem solving. So we are going to do a ton of stumbling our way through. Okay, let's jump into the first one. So we can take a look at problem 2. And I would like you to give that a shot with nothing else said. Okay, pause the video. Okay, we're back. So a couple things that I want to make sure we're good at. First off, our instruction changed. You've now been told to solve something, not simplify. You have to solve it. And for you to solve something, that means that you have an equation somewhere, and you can see you have an equation because of that equals sign in between. So your job is to solve that equation. That means you need to be able to tell me what is the value of x. We also have to make sure that we're going to do that exactly. No rounding off. Okay, if we were a little confused as to how to get things going or what the question was asking us for, I think that clarified a little bit. So I want you to give it another shot. Pause the video now. Okay, we're back. So the first thing that I just want to maybe kind of reference is this equation you've solved before. It just hasn't been this ugly. Like you've solved an equation where you had like a fraction plus a number equals another fraction plus, well, I need a variable in there somewhere, so let me just put in a variable on this one, let's say 3x over 7, something like that. Those are pretty equal in terms of what they represent. The given equation and the one that I just made up in blue. So I hope that we can see that our strategies should be the same. They might differ, but they should be the same. That I would hope if most people saw that blue, that because there was only one x term, then what they may do is they may want to get rid of that 5/3, collect, and solve. Great strategy. I also want to draw to your attention, though, that the given equation has a pile of variables in there. So what if I went back to that blue equation and I just tried to add in like another variable? Well, maybe your strategy changes now. That yes, you could go through and bring that x term over, get that constant over, and you could work to isolate again. However, I hope that we can see that partway down, we're going to have to get common denominators on both sides. That action may actually push us to try something different. I want you to take a look back at the given equation. And I just want you to notice that you totally have the ability to go through and get common denominators. Like right now, if I was just to put a wavy line down the middle, you should be able to collect the left side, collect the right side, and solve it using the exact same strategy. However, what I would like to show you is hopefully something that you would have done a little differently. Since the problem says solve, we're not dealing with an expression. Expressions we have to ensure are equal when we work with them. Within an equation, though, I have different options. I get to manipulate equations. So if I take a look at that equation, what I might want to do is focus in on all of these divide bys. If that was an equation that didn't have fractions in it, I could solve it so quickly. So if that's the case, then why don't I just get rid of my fractions? So what I'm going to do is I'm going to take a look at all of those fractions and I'm going to eliminate them. Well, to get rid of this first divide by, I have to get rid of a divide by x minus 2. That means I'm going to have to multiply by x minus 2. Okay, I'm going to get rid of that multiplication sign so we don't get confused. We all know we're multiplying. Well, to get rid of this divide by x plus 2, I would need to multiply by x plus 2. Well, and then to get rid of this divide by x squared minus 4, I would have to multiply by x squared minus... Okay, I would be 100% correct if I did that. That would eliminate all of my divide bys and I would have no fractions. However, I'm hoping that you might be able to look at that and realize I actually don't have to multiply by the green at all. Notice that my x squared minus 4 is x minus 2 times x plus 2. Just factored. That if I chose to multiply by that, then I will be able to eliminate all of my denominators. Okay, so I'm just going to erase everything that I put in that problem because now we have our strategy. So the first thing I'm going to do is I'm going to take that first fraction, x over x minus 2, and I'm going to multiply that by an x minus 2 times x plus 2. Now I have my 2, and I'm going to multiply that by my x minus 2 times x plus 2. Now I have my equals, and I have my old 5x, my 5x over x plus 2, and I'm going to multiply that by x minus 2 times x plus 2, and I'm going to multiply my old 3x plus 1 over x squared minus 4 by my x minus 2 times x plus 2. Now, I'm hoping that you can see that what I just wrote down there is the exact same strategy you would have used on that equation back in grade 9 or grade 10. Okay, I'm not going to do the multiply first because now that I've chosen that red expression, I know that that red expression will divide out in all cases. So let's go through and simplify each term. Well, my x minus 2 divides out my x minus 2, and my fraction is gone. My first term now becomes x times my x plus 2. I needed to go through and multiply what was remaining. Okay, I can get rid of that circle. Now I need to work on my next term. Well, my next term had no divide by. So I'm actually just going to simplify this and write down the x squared minus 4 just to be able to write down less. I'll expand my red. Now I take a look at my next fraction, and I can divide out my common factor of x plus 2. That leaves me with 5x times x minus 2. And in the last fraction, I love the fact that that whole thing will divide out. I can choose to factor the denominator if I want to, but I can see that those are going to be the same factors. So my whole last fraction simplifies to that. You take a peek at what you have on your page, see what I have on my page, and maybe we might look and see the blue might be a little more direct for us. We can now spend a quick line going through and expanding everything on the left, expanding everything on the right, just so that we can get down to being able to go through and say, okay, simplified on the left, simplified on the right, and now I'm solving a quadratic equation. I can picture everything going to that side. I would have a positive 2x squared, a negative 9x, and a positive 9 with nothing on the other side. Well, I can't put my x's together into one term, so I'm going to go through and hopefully factor. If that didn't factor, I'm stuck using quadratic formula. But I noticed pretty quickly that that will factor, and there is a 2x minus 3 times an x minus 3, and I can get down to x equaling 3 halves, or 3 as my two solutions. Whew. That was a good one. So as we work our way through, notice that the ability to work with all of our expressions is super important. That was really a grade 9 equation that was just made a little uglier by having a higher degree of x. Notice we didn't have to go through and keep our fractions around. However, the most important point about problem 2 was the instruction. That when I'm asked to simplify an expression, I do not have the ability to multiply something out, because then I would change the value of an expression. But since I had an equation, then I do have that ability to manipulate its value. Okay, hopefully things went pretty well with that one. We're going to get into some stuff that's a little uglier. Let's keep it going. Okay, take a look at what problem 3 is asking you. So I have given you this equation, 3x plus 2 over x minus 2 times x plus 2. It's equal to a over x minus 2 plus b over x plus 2. You have been asked to find a and b. So you have the correct answer to this when you can tell me what number does a represent, what number does b represent. Okay, I want you to go through and spend some time playing around with this one. Let's pause it now. Okay, we're back. So I'm going to argue we could have taken one of two actions on this one. That I would have had a bunch of people that on the right side would have said, I'm going to go through and add these fractions together. Or I would have had a bunch of people that said, hey, this is kind of like question 2. It's an equation. So maybe what I'm going to do is I'm going to multiply both sides, all my terms, by x minus 2 times x plus 2. It doesn't really matter what approach you take. Either the red or the purple were good. I'm going to get rid of the purple just because I want to make sure that we don't think that we always have to multiply out. Let's say that I did the red. So that makes my new top a times x plus 2 plus b times x minus 2. I'm assuming we can get a common denominator at this point in our unit. Well, maybe through reflex, we go through and we expand the top. So I get an ax plus 2a plus bx minus 2b, and that is all over that. Now, in terms of form, I shouldn't just be leaving that left side blank. There is an expression that's there. So I should be copying that down the entire time, even though I haven't changed it. Because there is something there, because it's not a variable, y equals something, but there's a full expression, I should be copying that down. Okay, I think we got down to a very good point. Now, just for anybody who was working on the purple, you will have gotten down to that same thing, just you won't have denominators. You'll simply have 3x plus 2 equals the stuff on the right. Okay, we get down to that point, and I think you've done some good work. I want you to pause it now, just in case we didn't get to that point, and I want you to try to problem solve from this point forward. Okay, again, your job, try to come up with what number A is and what number B is. Okay, pause it now. Okay, we're back. So this can become the challenging part to the problem. I'm going to call all that red mechanics. You're not sure what to do, but you have some operations you can do. So you take some actions and you go through some mechanical process. Okay, here becomes the problem solving. I'm hoping that we could see that, on that right side, you actually would reduce that further if you could. That really what we would do is our next line would, yes, still have the left side there. But if you could, you would collect your ax plus bx. If you knew what numbers a and b were, you would put those together. You would collect like terms. And you would also go through and collect like terms on your 2a and your 2b. Remember, a and b are both values. So 2a and 2b are really the constants. They're really just numbers in that expression. Okay, so maybe we get down to that point. Here's where our inspection comes in. Here's where our problem solving comes in. We could go one more line, and we could have the right side or left side. We can collect what we have on the right side. Some of us may be comfortable to say that if I take ax's and I add it to bx's, then I have a plus b x's. That if I knew what number a and b represented, I could actually collect them. So I would have the coefficient a plus b on my x's. And maybe we like putting that line down. Okay, regardless of how much work we show after that red line, it's still all going to drive us to the same spot. So I'm going to shrink that down a little bit just so we have a little more room. But this conclusion could have been made at any point with our final red line or the blue or the purple. We should be okay to kind of jump to this conclusion. That my A plus my B has to equal 3. And my 2A minus 2B has got to give me 2. Now, I just want you to take a moment and try to see if you can see where I came up with that orange from either the red, the blue, or the purple. Okay, pause it now. Okay, we're back. Now, I'm not going to ask anybody, okay, it's just up to you. You got to be able to see it. But what I'm going to do is I'm going to go back to our last red line. Okay, when we go through to collect that stuff, I hope we can see that my AX's plus my BX's have to give me my X term. They have to. And therefore, whatever the coefficient in front of the X, plus the other coefficient in front of the x has to equal 3. And that's how I can generate that first equation. Now you'll notice in the blue line or the purple line, we're drawing the same conclusion. Whatever A is plus whatever B is has got to give me 3. Or explicitly, A plus B has got to give me 3. And that gives us our first equation. Okay, if we're okay with that, then I want us to notice that we could do the same thing with our constants. That if I go back to my last red line, my 2a minus my 2b has to give me my number, my constant, my 2. You can see it a little more explicitly. 2a minus 2b has to come together to give me my 2. And then obviously in the purple. That's what gives us our last equation. Okay, we get to that point, and the rest of this should almost be shut your brain off mechanics. For us to go through, well, I'm going to call that first equation, equation 1, my second equation, equation 2, and we should be good to solve that system. So if I take a look right now, maybe I'm going to take equation 2, and I notice that I have a common factor of 2 in all of those. So I am going to divide that by 2 and reduce that fraction down to a minus b equals 1. So all I did was just divide everything by 2. You don't have to show me the divide by 2 there because we're simplifying. Well, now, between equation 1 and our new version of equation 2, maybe if I went through and I said, I'm going to take equation 1 and add it to equation 2, then I'll be able to eliminate my b's. So I take my a and add it to my a, so there becomes a 2a. My b added to a negative b, cancel out, perfect, that was the point. And my 3 added to my 1 gets me down to a 4. And therefore I can go through and solve that equation. There's my a equals 2. I like that because now I can sub a equals 2 back into one of my originals, and I'll go back into equation 1. That one seems simplest. So I have 2 plus b equals 3, and therefore b equals 1. So the question asked me to find a and b. I've now found a and b. I just have to state them in alphabetical order. So my a value is 2, my b value is 1. Nice. Okay, I'm hoping you guys can take a look back at 3, and you can see why that would be a problem-solving question for us. It's all based on the same theory, and the fact that we go through and we generate a system out of it, well, systems are something that you should be automatic with from grade 10. That's a nice cumulative sort of problem. Nice. Okay, we're going to leave the ugliest one perhaps of all for our last problem. Okay, you've got something in problem 4 that just looks so nice and easy to work with. Okay, the question looks like determine all positive integers for a and b that satisfy a certain relationship. And so you see a pretty easy relationship. 1 over a plus a over b minus 1 over ab equals 1. That looks an awful lot simpler than a lot of the stuff we've done today. Okay, your job, stumble your way through that one. Okay, let's pause it now. Okay, maybe we have no clue where we're going in this case. However, something might jump out at us. Like we should make a note that a can't equal 0 and b can't equal 0 within that equation, because then I would have undefined fractions. Now, that is not needed in this problem at all, especially given the fact that the question tells us determine all positive integers. And clearly, 0 is not a positive integer, but it might be something that we're kind of playing around with in our head. Okay, if we had no clue what to do, like we didn't even know where we were going with this, but we just said, okay, well, I know I can try some things, then my guess would be we might treat this an awful lot like problem 2. We have an equation, so let's get rid of all of our divide bys. That means that I'm going to multiply every single term by AB. And if I multiply everything by AB, then I know that all my divide bys will divide out. So pretty quickly, I can see that my A will divide out in the first term, my B will divide out in the second term, all of my AB divides out in the third, and there is no division on the right side. That red action will get us down to a B times 1 plus an A times A minus A1 equals AB. So we get down to that point, and now we have a much easier looking equation. We just might have no idea what to do on that. So we take a look at that, and at the very least, we can't put our variables into one variable term. So what we should be looking to do is to put everything on one side of the equal sign. Now, I might argue that maybe this becomes a pattern that you might like to put your things in each individual term, that we do kind of have a structure that we need to follow. It's not a strict rule, but whenever we happen to have multiple variables, what we like to do is we like to write them in alphabetical order, and if possible, we write them in descending order. But I would be able to kind of group, if you want to think of it, all 4 terms on one side of my equal sign. That would be the action that we would try to take. Okay, well now your job is anytime you can't collect your variables into one variable term, then we try to factor to solve. So we're going to try to factor that red line. Okay, well I have 4 terms. There is no common factor in all 4. So what I'm going to try to do is maybe, let's try to group it 2 and 2. Well, I can common factor out an A from the first 2 terms. That leaves me with A minus B. And I'm already seeing, well, that's not going to work well. So me factoring by grouping that way didn't allow me to fully factor the expression. Okay, so that didn't work. Now, it doesn't mean that my instinct was bad. It just meant that that means for me to go through and factor wasn't a good way to group. So I'm going to leave that on in purple. But I just want us to see so that if we look back afterwards, and I think that that would be a good thing for us to keep, that then we just saw that we tried something, it just didn't pan out. Okay, well that doesn't mean that factoring by grouping was a bad strategy. It just meant that maybe I grouped in a way that wasn't the most beneficial. So all I'm going to do is I'm going to try a different order. I'm going to try to put some things together that might allow me to factor in a different way. Well, I could do my a squared plus b minus ab minus 1, but I hope that we can see, okay, that blue is not going to give me anything that factors, because if I try to factor those 2 and 2, like neither pair has anything in common. But if I was to find my a squared and my minus 1, and I grouped those with my negative ab plus b, then I might find that grouping to be beneficial. So how can I how can I factor my first 2 terms? Well, maybe what I could do then is I have a difference of squares here, so I have an a plus 1 times an a minus 1. And now when I factor my last 2 terms, I have a b in both of those, so I could factor out a positive b. That would leave me with negative a plus 1. And I hope I can see that, oh, that was almost a great decision, but I can alter it. That factoring out a positive b caused me to have a negative a and a plus 1 on the inside of the brackets when I really wish that those signs were different. So if I factored out a negative b, well then that would leave me with a positive a and a negative 1. And now in my two terms, I have a common factor of a minus 1. So I'm going to factor out my a minus 1 from both terms, and that's going to leave me with an a plus 1 from the first term and a negative b from the second term. Okay, so what does that mean for me being able to solve? Well, I now at least got it down to a product equal to 0, so I know that one of those has to equal 0. So you can choose to put this line in if you like, that a minus 1 must equal 0, or a plus 1 minus b must equal 0. Now, for most of us, we're going to go through and we're going to skip that line, and we can probably jump straight to a therefore a equals 1. So I have a solution there. I take a look at my next equation, and I don't even really know how I want to write that. Like, I could write that my a value is going to equal b minus 1, and I could choose to write it that way. Or if I wanted to, I could choose to write it solving for b, that my b value is equal to a plus 1. It doesn't really matter how I want to write that. I can solve for either variable, because if I go back to my original question, it wants me to find values of a and b, all positive integers for a or b that satisfy that. Okay, so the first thing I found is that my a value could equal 1. Okay, so let's look at that scenario. And I'm just going to number it so that we can kind of examine each of them. My a value could equal negative 1. Well, if a equals negative 1, if a equals 1, what does that mean for my b value? So I could sub that into my other green equation. So that means then that 1 plus 1 minus b equals 0, so my b value is 2. So I just found one relationship that would make that equation true. Therefore, a is 1, b is 2. Now, my other relationship could come back to my blue or my orange statements. I'm just going to shrink this down a little bit to make sure it fits onto our screen. But those blue or orange statements talk about a relationship between A and B. And so if I was to examine, let's just take the blue. The blue's nice and easy. That when I have my A value is equal to B minus 1, then what that talks about is the way A relates to B. Notice that my A value has to be my B value subtract 1. So we see our B subtract 1 equals A. So if I look at that, in order for me to get my A value, I have to take my B value and subtract something from it. That means that my B value has to be bigger than my A value because I take away 1 to get it. So I could now just interpret that as a statement that my A value has to be my B value subtract 1. Therefore, my A is 1 less than my B. My A has to be 1 less than my B value. Now, do a little check. So for instance, if I was to make my A value, I don't know, pick some number, 4, then my equation becomes this. I'll notice my B value then becomes 5. My A value that I picked was 4. I solved for my B value of 5. Therefore, my A is 1 less than my B. Now, if we struggle to see that, take a look at your other expression. Let's jump back into our orange equation. You'll notice there it explicitly says that my b value is equal to my a value plus 1. Some people might find that easier to interpret. You can see that you take your a value and you then add 1 to it to get your b value. However we want to deem that, your a value has to be 1 less than your b value. So, I just want to make that a little more formal. So let's get rid of the statement of my b value, and we can state that our a is 1 less than b. So how can we now make an overall statement? We can now say, therefore, that when b is 1 more than a, or a is 1 less than b, however you want to state that, with one extra little restriction, that as long as my b value is greater than 1. Notice that if I allow my b value to equal 1, then back up in this equation, I'm going to get an a value that equals 1 minus 1. That's 0, and 0 is not a positive integer. But if I put that restriction that my b value is greater than 1, then I have my case for all positive integers. Okay, I'm hoping we're taking a look at that and we realize that, boy, that one was a doozy. Okay, that is probably as tough of a problem-solving question as I think we can kind of work our way through given the material we're working with. That is, we've got some exposure now to some rational expressions. We can work through them in an equation. And I can ask you to now work through some system stuff as well to maybe stumble our way through a couple cases. So the job for today is to take a look back at probably the first 5 problems. I don't know if I would throw problem 4 in the same mix, but you can look through the first 3 kind of mechanical problems, and then probably your next 2 sort of problem-solving situations. And I think that that should give you a good basis of where you can go with this stuff. Okay, your job is to make sure that you're pretty automatic with what we had on the page today, and then to be able to jump in and play around with some of your practice. Okay, good luck.